So, welcome back to the second session of this lecture on scattering matrix parameters. We are going to continue from the previous session. So, in this session we are going to investigate the unitary property of the scattering matrix. For that, we would make use of the power conservation theorem. Now, the power conservation theorem states that which physically essentially means that the sum of the incident power is equal to, which is appearing on the right hand side, is equal to the total reflected power, which is appearing on the left hand side. So, now we know the outgoing wave at the nth port is related to all the incident waves at other ports through this relationship, which we can obtain from the scattering matrix definition, from the definition of the scattering matrix parameters. So, therefore, the power conservation can be expressed as all we did was substitute from V n minus here, that is the left hand side, so therefore, by substituting from V n minus from this equation to that equation, we simply obtain this equation. Now, because this is, we have no restriction on the choice of V n plus, okay, we will choose all V n plus to be 0 except at the ith port. So, before that, let us give a number to this equation, that is 3. So, then choose choose all V n plus equal to 0 except V I plus. When we do that, because we are in nobody has restricted us from choosing the V I plus, V n plus, that can be chosen according to my free will. So, then from 3 we obtain So, now we can see from 4 that okay. So, cancelling V i's mod V i's plus square on both sides, we obtain this relationship, and that can be also written as where SNI star is the complex conjugate of SNI. So, this equation 5 holds good for any I. Okay. So, it holds good for any I. So, what does equation 5 state? It states that the product of the scattering matrix parameters of one particular column times the complex conjugate of the same column, if I add up the entire column like that, the column multiplied by the complex conjugate of the element of that particular column and add that up, the sum is going to be equal to 1. In order to go to the next phase of the relationship, particularly to find out what happens if we do not choose one particular column, if we choose two different columns, what is going to happen? We go to the next proof, and for that we will choose all V n to be 0, all V n plus to be 0 for all n except n is equal to S and R. So, we write that so, this is chosen. Then if we apply the same relationship 3, if we apply this relationship which is the general relationship, we can obtain okay. Then we expand this part, we expand the left hand side, and when we expand we get So, we name this equation 6. Now, we know from equation 4 that these two terms which we are writing we know this from equation 4. Okay. So, let us go back to equation 4 from this equation. Okay. So, we can write these two quantities, and therefore, now 6 leads to some cancellation. So, the two terms are going to cancel on the right hand side, and we are going to get those the product terms. Let us write this in the same way. Okay. Or we can rewrite this as taking the voltage variables all together to one side. So, we put this as 7. Now, these two quantities Vs plus Vr plus, these two quantities again can be chosen according to my free will, because they are general. This equation will hold good regardless of the values of Vs plus and Vr plus. So, let us first choose Vr plus equal to Vs plus. So, let us choose Vs plus equal to Vr plus. So, when we do that, equation number 7 can be rephrased as so we call this equation 8. Now, we make the next choice, that is Vs plus is j Vr plus. If we make this choice, then we get from equation 7 again. So, we call this equation 9. So, because neither of these two quantities Vs plus or Vr plus, they are neither of them are 0. The only way both these equations can be satisfied is given by the following condition, and that is so, I repeat again that because Vs plus and Vr plus none of them are 0, the only way equation 8 and 9 can both be satisfied is by setting SNS SNR star summation over n equal to 1 to capital N as 0 with S not equal to R. So, this constitutes the second condition as to what would happen if I multiply different columns of the scattering matrix. So, it says that the product of a particular column and the complex conjugate of any other different column, if I add those results together, if I add those products together, that will be 0. So, this is the second important property of the scattering matrix. A matrix which satisfies these conditions is called a unitary matrix. It is called a unitary matrix. So, this can also be established by using matrix algebra, and that is, if I write the power conservation theorem, in the matrix form, if I write it in the matrix form, and I can write the right hand side as okay, and this can be written as from which I can write Now, because this matrix is not 0, the V plus matrix is not 0, the only way this can be satisfied is this becomes 0 or we call this equation 11a, or we can write this as we write this as 11b. So, basically we can obtain the same unitary characteristics from these expressions. (11b) is the definition of a unitary matrix. So, this is the definition of a unitary matrix. And the conditions 5 and 10 we discussed before, the conditions number 5 and 10, they can be obtained by performing the matrix multiplications in equation 11a. Okay. So, that is all for this session. We will continue.